fancy functions by using basic arithmetic operations, plus, minus, and multiply, and so on and so forth. Okay, so you know the exponential function probably is computed by taking 20 terms and then throw away the rest. So you'll be wondering, if I do that, how big is the error, right? You will want to know beforehand, can I have a bound on the error? Do I know for sure the error is less than something so I don't make big mistakes, right? So we talk about error analysis a little bit today for Fourier series. Oh no, Taylor series, sorry. Okay, so we'll put back Taylor series. So Taylor series for function f of x, let's write it down. I kind of memorized it after writing it so many times. Okay, so that's the Taylor series, f of x expanded at c, about c. Okay. So and when you do it in your computer, of course, you never go to infinitely many terms. You will cut it off. You will just take the first some terms, first n terms. So there's the expression, we call it a partial sum, right? I take, let's say, first n plus 1 terms. So I'll be taking only n plus 1 terms and throw away the rest. So we call this partial sum, give a name, fn of x. It equals to the same thing, but I will be summing from 0 to n. N is a number, 100, and then I stop there. So okay, so I'll be interested in if I use the fn to approximate f, how big is the error that I'm introducing? The error would depend on n. In what sense, right? Okay, so let me give you, this is the one version of Taylor's theorem. There are a couple of them. Okay, so the arrow, let's say it carries an index n plus 1 by taking n plus 1 terms, will be the function minus your partial sum. Is that right? I look at the difference between them. Okay, so what would that be? Well, assume your Taylor series converges. This is the infinite sum, and this is the finite sum. I kind of chop it off after n plus 1 terms, and I throw away. How many terms am I throwing away, not taking with me? Infinitely many, right? So it's still a sum k from n plus 1 to infinity. Is that right? So many of them. Then you're freaking out. You're worried. Oops, will they add up to be a finite number? What happens? Will they be sufficiently small? Okay. So you have infinitely many terms. So let's look at the leading term. Let's take a look at there. There is the leading term. That's so important here. So let's say the first term in this series, meaning k equals to n plus 1. What would that give me? Is 1 over n plus 1 factorial, right? F to the n plus 1th derivative at c, x minus c to the n plus 1, right? That will be the first term in this infinite series, right? So Taylor's theorem say, which we do not prove here, provided convergence, assume this converges, then this infinite sum is dominated by the first term, okay, in the following way. Let me write it out. So this is equal here. It's not even an estimate, it's exact, okay? So 1 over n plus 1 factorial f to the n plus 1 derivative, okay, I sneak in something different, psi x minus c to the power n plus 1. This exactly, the arrow equals to that. What is the psi? Let me see. specify for there exists some psi. I might not know exactly where it is, okay, but I know it exists, and it lies between x and c, somewhere between x and c. Could be x and could be c on that interval from x to c. Okay. Now proving this requires a lot of work. It's not what we will do here. So what I will do now is to explain this theorem maybe geometrically to have an understanding of, in the simplest possible case, it makes sense. Let's check that. So simplest case, you can think about, well, the lower the n, the simpler it is, right? So let's say n equals to 0. When n equals to 0, if I want to write out my Taylor theory, how would it look like? So the arrow now will be fx minus the partial sum, right? If n equals to 0, I would take only one term. That would be the first term, right? That would be the f of c that I'm taking. Is that right? And that arrow equals to this expression setting n equals to 0. So it's 1 over 1 f prime some psi times x minus c. Agree? So f prime of some psi x minus c. That's the Taylor series with n equal to 0. Okay? So, okay, let me write it again here. For some psi between x and c. Okay, so let's see. Does this look familiar, that expression? What is saying here? How about let's say x does not equal to c. If x equal to c, it's trivial, the arrow is 0. Let's say x doesn't equal to c, so I can divide both sides by x minus c. I'll have the following expression on the left, right? And then on the right is some f prime of psi, for some psi. So what does that mean? Let's draw a picture. Say I have some function f. How wild do you want it to be? Some function f, continuous, differentiable many times. I have to make it smooth. Okay, and I have an x. Let's say this is my x, and I expand it somewhere. Let's say that's my c. Okay. So what's on the left-hand side? In particular, the quantity on the left-hand side, what does it have to say to the secant line connecting these 2 points? Say it again.
The tangent?
Just the slope between the lines.
Is that right? Do we all see? The y difference between the 2 points divided by the x difference between it. It's the slope of this secant line. Is that right?
So the tangent.
So yeah, so what it's saying is that there exists a point psi that lies between x and c such that the tangent is parallel to this line. Is that right? So you take this line, parallel, you move it up here, you will find somewhere it will touch the graph 1 point. That's tangent. Then the derivative right there equals to the slope of this line. So that will be your psi. There exists at least one. So it has a name, this property. Anybody? It has a dramatic name. Not the intermediate value theorem, something, the mean value theorem. Is that right? Nothing mean about it, but okay, that is actually Taylor theorem when n equals to 0. Now, if you put n equals to 1 or 2, it's harder to draw a graph and see what happens, okay? But here it's very clear for n equals to 0. Okay. Is that okay? Okay. So that's on Taylor series. Okay, so now next I will talk about something called numerical differentiation. So you have a function and you want to compute its derivative, and the function might be not so easy to differentiate theoretically, so you go to the computer and say, give me a good approximation, I'll be happy with it. Okay, so the name for these methods, maybe you have heard, I don't know, they're called finite difference. Okay, and I will use the shorthand FD or FDM, finite difference method, for it. Is okay? So you have a function f, so you want to approximate, the whole idea is to approximate f prime at x. How do you do that? Okay, so we'll talk about 3 different methods and we'll analyze them. So the first one is f prime of x is approximated by the following: f of x plus h minus f of x over h. And this is called forward Euler. It's due to Euler. It's an Euler's method. Okay. And then the second one is to use informations backward: f of x minus f of x minus h over h. Okay, so you take information on the left. If you think x is time, that's like from the past. So this is called backward Euler. Okay, and the third one is a kind of a more centered one. So I will take information from both the left and the right. Okay, so I take something on the left, I take something on the right to compute something in the middle. So that's called a central method. So central finite difference. Okay. So before we dive into the analysis, let's take a look intuitively to understand that these actually give us an approximation for h small. So I forgot to say, you have to give me an h which is positive and which is small. Okay? If h is very large, it's not a good approximation. Right. Okay, so let's try to see why one can do so. So let's draw a picture. I'm going to make it more. So this is f, let's say that's x, and let's say I have a convex function like that. And I want to find, for example, this is my x. I want to find the derivative there. So you know the derivative is the slope of the tangent line, right? So right here it looks like almost like horizontal, but probably not really. So that will be the tangent line, so I want to find the slope of it. Okay. But theoretically, maybe the f is really bad. I cannot differentiate, so I go for finite difference. So I will illustrate the idea with a rather big h. Otherwise, if I draw right next to it, you don't see what I'm doing. So we zoom in. Is that okay? H is small, okay, but we just zoom in and draw it big to get the idea. Okay, so x is here, x plus h is here, the distance is h, okay, and I find the corresponding point, that's my f. So what is the forward Euler computing? What's that expression? F of x plus h minus f divided by the distance between these 2 points, slope of the secant line, is that right? So I connect these 2 points, let's see, and the slope here, I use it as an approximation to the slope here. Okay, it doesn't look very good here because my h is big. Imagine this point is pretty close, and then those two slopes will be almost the same. Agree? Is that a reasonable one? So this is the forward Euler approximation. Okay, so the backward one will be, I take from the left x minus h, and this is h, and that's the point where the function is. So it's a similar idea. You'll be taking these 2 points and draw a secant line and say that the slope of this is a good approximation for h small. We see it's reasonable. Do we agree? Okay. At least from the drawing I have here, maybe I purposefully choose it. You see, forward Euler will give you an approximation that's a bit too big. And the backward Euler will give you an approximation that's a little bit smaller than the actual value, right? The slope is smaller here. So let's take a look at the central find the difference. What does it do? It takes this point, x plus h, and takes that point, x minus h, the y distance between them divided by the x distance again. So it's taken a secant line that goes through these 2 points and say the slope of this guy, that's center finite difference, say the slope of this line is a good approximation to the slope of that line. At least in this picture, that guy looks better than the other 2 choices. Do we agree? They seem to be a better one. Okay. We'll do some analysis to that. Leave the Taylor series over. Okay, so I want to show you this way of making analysis. So arrow analysis, how big is the arrow? And in particular, we'll learn how to the order of the method. Okay, so we'll write out Taylor series again. So Taylor series for, I want to expand this function f of x plus h about x. Okay, so I think x now will be the c here where you expand, and I want to find the function value at x plus h. So the x here will be x plus h. Are we okay? So take this Taylor series, change c into x, change x into x plus h. Okay, so what will be this term now? X plus h minus x, this will be h. How far away you are. Okay, so I'm going to write out. So f at x plus h equals to summation k from 0 to infinity 1 over k factorial f to the k derivative at x times h to the k. Okay? It's another way of writing the same thing. But in numerical analysis, Taylor series always takes this form. And with keep in mind h is very small. Okay? Well, I can write out a few more terms. Let's say if I write out the first term, it will be f of x. The second term will be h times f prime of x. And then I'll have h squared half f double derivative of x plus, okay, take one more term, 6f double triple derivative of x plus. There are infinitely many terms, right? So from the Taylor theorem we just presented, if I chop off here and just write all the others as one term, it's dominated by the leading term, which contains h to the power 4, right? Times some constant. So I'll introduce you this notation. A fancy O, okay, of h to the 4th. So what does that mean? This notation denotes some quantity which is bounded in absolute value by a constant c times h to the fourth. Is that clear? So this one is a quantity, some quantity bounded by c times h to the fourth. C is just a constant. Is that okay? Have we ever seen such notations of order? O stands for order. So what matters here is not the constant c, it's actually this number. You think about it. If h is really small, say 10 to the negative 4, then h to the third or h to the fourth makes a huge difference, isn't it? It's much bigger than the c is 1 versus is 10, right? That doesn't make such a huge difference. Okay? So that's that, and I will write also x minus h expanded x. So it's the same expression here, and you can substitute h with negative h. Okay, so I'll write it. Okay, I'll stop here. I just say whatever comes after is of order 4. Or I could have stopped here, and then I could have write of order of h squared to lump all the rest. You can cut it, truncate it, wherever it suits you. Okay. Okay, so now we'll be computing something called local truncation error. So let's do the forward Euler. Once you've seen one, you know how to do the rest. So forward Euler. Okay, so I want to see the expression here on the right hand side. My goal is to show that this expression equals to f prime of x plus arrow. And I want to know how big is the arrow. In particular, what is the leading term in the arrow? Because that dominates, right? Okay, is it clear? I know sometimes this is not so obvious. Okay, so let me write out the forward Euler. So what I will do, I will put in the Taylor series that we just worked for f of x plus h and put it in there. Okay, so this gives me 1 over h, okay, so which we prepared. So this is f of x plus h, f prime of x plus h squared half f double prime of x plus, let me be painful and write that. Okay, all these terms plus something of order h to the fourth. That's what we set up. And then minus f of x. Is that right? Okay, I just copied some cancellations. You know, this cancels that. And I can distribute 1 over h onto every term. So what do I get? This h cancels. All the h is reduced by power 1. This is c times h to the fourth, and now becomes h to the third, right? So I have f prime of x plus h over 2 f double prime of x plus dot dot dot. There'll be many, many terms, but I don't need to, because all I care about is the leading arrow. Provided it converges, all the rest is dominated by this term, right? So the notation now will be f prime of x plus, you want to look for the h. You want to see what is the exponent on this h. And the rest is just constant. So this is bounded by some constant times h to the power 1. I just lumped them with this notation. Is that okay? Okay, so this arrow is called local truncation arrow. the local comes from the fact that it works for h small. If h is big, it doesn't make sense. Okay? H has to be small in the small neighborhood around x. So it's a local analysis. You don't go far away. And the truncation arrow means basically the analysis is done by cutting off Taylor series, just truncate it and say the rest don't matter. Okay? So that's why the name. And now you see the forward Euler is approximating f prime of x with arrow of this size. And what matters is the exponent on the h, right? If it's 1 or 2 or 3, makes a big difference. So that number there gives you the order of your method. So this is a first order method or approximation. Is that clear? Okay. Now I want to do, backward Euler, you can carry it out in the same way. You find out it's a first order method as well. And from our analysis here, it seems like the central final difference looks like a better way of doing it. And let's get that verified and see it is actually higher order. Let's try that. Okay, so I will do it here. So the central finite difference. So let me write it. It's 1 over 2h of f(x) plus h minus f(x) minus h, right? So I throw in the Taylor series for this and for that. Let's see, what do I get? 2h. So this will be f of x plus h f prime of x. You could probably see it. It just takes me longer time to copy it down. H third, 6 f triple derivative of x plus many terms. Or I can put the order with me, but it's okay. So this is subtracting this expression. I'll put it here. Make sure I change all the signs. Many times. Is that okay? So some cancellation, of course, takes place. These two terms cancel, and this term cancels that. Is that right? And these two terms can be combined into f prime of x. Is that right? And then these two terms can be combined, will be h third of 3 f triple derivative of x plus all the rest will be higher order, h to the 4th at least. Okay, so what do we have? Let's divide it by 2h. So I have f prime of x plus. So if I divide this term by h, what do I get is h to the power 2. Is that right? Times some constant. And that's the dominating term, right? That's the leading arrow term. So that gives me the order h squared. Whatever comes behind is dominated by that term. Okay, so you see the leading arrow is of order h squared. So think h is 10 to the negative 4. That's how small your step you take. Then forward Euler will give you the arrow 10 to the negative 4, and the central difference will give you arrow 10 to the negative 8. It's much better, right? So the exponent is important. So this is a second order method. Yeah. Is that clear? Any question of how to carry out this computation of finding the local truncation arrow? Is it clear? Okay. Tangled. Alright, so I will give you one more final difference, which is very useful later on when we get into differential equations. That is how to approximate a second derivative. Okay. Later on we talk about differential equations, Laplace equation, heat equation, there's second derivative. So this is done by a central final difference in this way. Okay. So it takes 3 points, x, and to the left x minus h, and to the right x plus h, and do this computation. Okay. So I could put it in as a homework. It's on my notes also. You can throw in the same computation, put in the Taylor series for these two, and cancel out terms and look for the leading arrow term, and you will find that this is a second order method. Okay? I will not go into the detail. It's repetitive. It's the same thing. Yeah. Is it clear? Any question? Yeah?
So, can you just decide what you want the error term to be by just expanding it out farther?
You mean, can one find even a higher order, for example, to approximate f prime of x? Yes. You take more terms. Yeah.
So whenever you say that the second derivative is a second order method, is that just arbitrarily chosen?
Of course. You can be 4th, 5th, as long as you're willing to do the work and take more terms. Yeah. So the way to find out the order of the method is what we're learning today. Taylor expansion, and then see how many terms cancel. What's the leading arrow? That tells you the formal order, right? Provided the function you're trying to differentiate is differentiable at all, right? Mm-hmm. Okay. Okay. Let's go into next chapter. I want to start a little bit. Okay, so I usually start this course on this topic, polynomial interpolation, because it's a very important building block in many of the things that we will do later. So it's very nice to have that done first. Okay. So let me set up the problem. What we will be studying is the following. So I have a data set. Labeling is always a bit annoying. So I have n plus 1 data points. Okay, so let's say, just say it is xi, yi. One x value corresponds to y value, okay? And I have the index runs from 0 to n. So there's n plus 1 of those points. There are. Okay. And then a little bit careful, you have to put some restrictions on your data set because x is an independent variable. You still want a continuous function because you're interpolating it with a polynomial. So these xi's shall be distinct. If they are the same, then your function will have a jump and it doesn't make sense. Is that clear? So possibly all these xi's shall be distinct. And they could be sorted and they don't have to. That doesn't matter. Okay, they have to be distinct. Okay, and then our goal is to find a polynomial of degree n. Okay, and what do we say? Call it Pn of x. N is the degree of the polynomial, such that it interpolates the data. So what does it mean? That means if I put in xi, my polynomial returns the value exactly yi. So if I plot the polynomial will exactly go through my n plus 1 points. Is that clear? All right? So I from 0, 1, 2 to n. Okay, so polynomial of degree n. Let's write it out. The most general form. Okay, so it matters that we have these coefficients, doesn't it? an so if you have a polynomial of degree n, you know you need n plus 1 coefficients, a0, a1, a2, all the way to an, right? Once they are chosen, you have the polynomial. It's determined, right? So your job now is actually to find those coefficients, isn't it? Okay, so this is our goal here is to find these coefficients, a0, a1, all the way to an. So now you have a problem here in the end which contains n plus 1 unknowns. Think about it. I didn't write out the detail, but think about it. I have n plus 1 unknowns. What can I use to find these unknowns? How many conditions am I given? Well, it says it has to interpolate these n plus 1 data points, isn't it? Each data point is a constraint. It leads to an equation. I will have n plus 1 equations, right? Matches the number of unknowns. Okay? So before going into the general setting, we'll take one specific example today, just to get a feel of it. Okay, so very simple example. Oh yeah, I forgot to ask you, anybody wonder why do we do this? Is there any point of doing this? Why do we need to interpolate a data set with polynomial? Any motivation that you think this can be useful?
If we need to estimate value given some other point that we don't know.
Exactly. Say you did an experiment, right, which only allow you to collect a set of discrete data, something that changes in time. What if in the intermediate time I'm curious what it is? This gives you a way of finding it, right? Other ideas?
Testing out physical laws that should give you certain polynomial relationships.
Okay, so if you know a priori it's a polynomial, you get some points, you can identify that polynomial. Yeah, that's a very good idea. Anything more? So what's so great about polynomials?
They're continuous.
They are?
Continuous.
Okay, but sine, cosine, lots of functions are continuous. What do we really know about it? If I give you a function, it could be continuous, but it could be very nasty. I ask you to do integration, differentiation. You want to find the exact expression, it's a headache. And then if you just want some approximation, well, you can generate a set of data of this function at certain discrete points, and then you interpolate by a polynomial. Hopefully it's accurate, then you can deal with the polynomial, because differentiating or integrating a polynomial is so easy. Agree? Can that be a good motivation? Okay. So keep those in mind so we be motivated. Okay. So I'll give you a data set today just to set up the idea. xi, yi. Let's say 3 points, 0, 1, 2/3, 1, 0, and half. Okay? Okay, secret, don't tell anyone. This is cosine of x over 2. But we don't know. If you throw that in, that would generate this data. So we're going to throw in a polynomial to interpolate and see how well the polynomial approximates this cosine, which is a continuous function, infinity. Okay? So what do you do? So P2 y equals to P2 of x we want to find, isn't it? A2 x squared plus A1x plus A0. My unknowns are those coefficients. I need to find these 3 coefficients by solving 3 equations, right? So I'll set up the equations. Okay, so the first equation is when x is 0, y is 1. We're okay setting it up? So I'll have a2 times 0 squared, a1 times 0 plus a0 equals to 1. You already know a0 equals to 1, right? I just carry the 0, so you see what's in general. So second one, x equals to 1. So I have a2, 1 squared, a1, 1, a0 equals to 0. You see that? And the third equation, x equals to 2/3, y equals to half. Okay, so that will be a2 times 2/3 squared, a1, 2/3, a0 equals to a half. Okay, you have 3 equations, you have 3 unknowns. Tell me, are these equations linear? In the unknown?
Yes.
So, you have MATLAB. How can it help you? Can you write this into ax equal to b? Are we all okay in that? So, let's write this. Once I write it into ax equal to b, I just give it to MATLAB and say, solve it for me, right? So, ax equals to b. Okay, let's draw this matrix. And the x is the unknown, and the right-hand side is b. Are we okay? So now my x here is a0, a1, a2. It doesn't matter. I could have put a2, a1, a0. It's okay. So the right-hand side is 1, 0, and half. How do I fill in the A matrix? Are we comfortable doing this? So what will be the first column? It should correspond to a0. So it will be all the coefficients in front of a0 that you copy it down, right? Which will be 1, 1, 1, right? What's the second column? It will be a1. What's in front of a1? Well, it's 0, 1, 2/3. But you know this is x0, x1, x2. Do we see the pattern? Let's put in 0, 1, 2/3. So what's the third column? What's in front of a2? Do you see? x0 squared, x1 squared, x2 squared. Right? Those numbers are dummies, right? Agree? So 0, 1. Okay, let's put in the numbers. They're not dummies, they're important because I need to solve it. You type in this matrix in MATLAB and ask him to solve, and he'll give you the answer, okay? So, or if you are geeky, you solve the first one, a0 is 1, plug in, you reduce it to a 2 by 2 matrix, right? That's much easier to handle, right? Okay, so a0 is 1, a1, what would that be? I really worked it out, you know? Is negative 1/4, and a2 will be negative 3/4. And put them back, and you can have your polynomial. Do we want to write the polynomial? Okay, let's do that. So in the end, this is the answer. This is your polynomial. a2 is negative 3/4 x squared minus 1/4x plus 1. Yeah. So next time we'll look into a general situation, n plus 1 point. Yeah, question?
There, where that's P2, where does P2 come from? Was it y from P2?
Oh.
Yeah, how do you decide?
Oh, because you have 3 points. N plus 1 point. You need to fit in the polynomial of degree n. Is 1 less than the number of points.
Oh, okay.
Always.